So during the entire conference, we have heard a lot about Apache Iceberg, right? What it does, what it's used for. But I think one initial conversation we had in the first data lake session was also about table maintenance, right? And it's very important to keep your tables optimized and how you can keep getting the best performance that you can, right? So that's the topic that we're going to discuss about today. So just to start with, so I'm Akshat. I'm a product manager in Cloudera's open data lakehouse, managing Iceberg and a few other stuff. Before getting into product, I was a senior engineer and contributing to Apache Hive and Thales. And with me,
My name is Attila. We already met together today, and yeah, I'm also working for the Cloudera.
thank you. So, so today we'll have certain topics. First, we'll understand what Iceberg does. We already have built some understanding of what Apache Iceberg is, what it does. So we'll just quickly browse through that section, then talk about their Iceberg's architecture overall, why table maintenance is needed on Apache Iceberg, why it's very important, when do we need to run table maintenance, and how to run table maintenance, right? So yeah, what is table format? Before getting into Iceberg, we need to understand what table format really is. And this is where I always like to start with a quote that don't forget the OG. And OG is Apache Hive. You want to talk about
No,
Hive?
so it is actually we have the original actually from the Apache Hive, and also the Apache Hive has one of the first table, the Hive table. And many, I would say, customers and even the community has some kind of problem with the original Hive table, how it is designed. And also if we are looking back the how the Hive table is designed, and also there are pros and cons around it. But this was one of the first table. It is coming, actually, it is already a decades old of this type of table. And don't forget, and yeah, it has some problem for sure, but also this was the pioneer of the table format. This was the first one that is created the first table format, even from the external part. Even actually we have some kind of love and hate I would say, feelings around the Hive acid table. But nowadays, as I mentioned in the previous presentation, we are focusing on the iceberg table, not the acid tables anymore.
So it does have pros and cons, as Attila also mentioned. So some of the pros and cons are written here. Given that it was a very first table that all the engines started to adopt, one of the key benefits or pros, what it's very effective, right? In full table scan, it makes queries very well. It's file format agnostic. Customers can bring in JSON, CSVs, Parquet, Avro, ORC, and whatnot, right? So it used to be the single central answer to what data is in a table. And given it was very initial, right? It's the de facto for all the engines. So Spark supports it, Trino supports it, Hive engine itself supports it. So
Impala.
yeah, so a lot of support. But there are cons, right, of this design, that due to this design, you see data files are under folders, right? So smaller updates, if you want to do that, it's very ineffective, right? Even with ACID, it's not very performant. So there's no way to change multiple partitions safely. You have to keep on bringing more partitions to your table, which affects the performance overall. In practice, multiple jobs modifying the same data set don't do it safely, right? So all of these were some of the cons that we wanted to address with a new table format. So let's say we do not have Iceberg. So what were the goals of Iceberg, right? What were the goals that we wanted to achieve with Iceberg? One, we wanted a table that is correct, right? Which maintains the consistency of the data. The query planning needs to be faster with execution, right? It needs to allow users to not worry about the physical layout of the data, but just the metadata, right? Overall, just they want to query, simple. Table evolution, I do not want to rewrite the complete table just because I want to evolve or my business needs are changing. So I need to either create a new table or create a new partition. No, we just want to simplify. I want one table with evolution to it, right? And while we are doing all these things, we need to make sure that we are doing it at scale, right? So that's where Iceberg comes into picture, right? So we have a lot of discussions with customer, and customer asks what is Iceberg, right? What is Iceberg and what it really isn't. So Iceberg is just a table format specification. It tells you how to read it, how to process operations on top of it. It's set of APIs and libraries. What it is not, it's not the storage engine itself. It does not store the data anywhere, right? Like it's just a table format. It's not an execution engine. Iceberg is not reading anything. Its execution engines are Spark, Trino, and it's not also service, right? So just to clarify, just putting it out there. So so if you see the older, this design, right, is what Iceberg provides. You have your data files. What Iceberg really brought to the table was the metadata layer. We'll discuss more about it in details a bit more. But here are the design benefits that Iceberg brought to the table, right? It makes the smaller updates very efficient. How? We will discuss in the architecture. It makes snapshot isolation for transactions. So read and write do not interact with each other, right? And all the writes are atomic and concurrent. Faster query planning, because now all the metadata is staying very close, and the query engine just read the metadata and plan queries much faster. It's engines can see the changes very immediately because it's snapshot isolation and abstraction of physical layer from the logical layer, right? So this is how it's making it possible. Yeah, this is
What's already seen?
yeah. So I'm pretty sure like you have seen this slide multiple time, or this architecture multiple time. There's no Iceberg conference or Iceberg discussion without this diagram. So what Iceberg really brought to the table was this metadata layer. So there above, there's a catalog, but I've removed that for now. But focusing on the metadata layer and the data layer, this is where Iceberg brought the revolution, right? And then thought leadership and the design. So now you have metadata files which records each snapshots. Every change here is a snapshot 0. So let's say if you are at snapshot 0, you inserted new data into your table, it will create snapshot 1. Snapshot 1 will refer to its manifest list, which will contain the list of manifest files, which also have some metadata about the partition details and all those things. And then finally your data files, the actual data files, right? It created this infrastructure of metadata on top of your original data files which were missing, right? So while you have these things, imagine the expansion at scale, right? As you scale, these metadata will also keep on growing. Every insert will bring on new snapshots, new manifest lists, new manifest files, and data files will keep on increasing. That's given, right? But with Iceberg, this layer is also increasing. And this is where table maintenance is very important, so that this is very fast to query for query planning, query processing, and so on and so forth, right? So before we go into
So just I would say the example actually from the real life why we need actually table maintenance. So it is these things that you see here, manifest file, whatever, and also you will see many data files that it has to be way more, I would say, bigger and efficient, and has to have some kind of strategy. But this type of table maintenance, it is also happens not just on the big data world, but also in the human life as well. When you are sleeping, so this is, I would say, a real example or a practicing example. So when you are sleeping, this is when your brain is starting to have a table maintenance in your side. It is starting to, every single day you have something that you see, smell, eat, have an experience, it is storing into your brain. And when you are going to sleep, it is going to have, I would say, move from one set to another to have some kind of, I would say, structural way. And that's why so many people, it's after learning something and wake up, has some kind of memories. And if you do not have this type of table maintenance, eventually 6 days later, it will be, the human nature is going, the human part is going to be die because of the needs of the table maintenance. Big data is the same thing. If you have many writing part, every single day you have something that you write. And if you do not maintain your table, eventually the table will be unusable and you are not able to query, and your cluster will be failed. So this is something, the same thing. And you can, in the next slide, you can see that how many type of part where we need to think about it. It could be in a manifest file, data files, also there are snapshots, and one of my favorites is the orphan files that could also be there, where we need to maintain our data. If you do not do this, your cluster will be slow. And one thing that is, I would say, the cons to compared to the ACID tables, the Iceberg table, if you do not maintain well, it could be eventually, or within a very short period of time, it could be very, very slow, and you can say that, okay, I moved to Iceberg, why my query started to be slow? Because of this missing of this table maintenance.
Definitely.
But let's start actually with the first one.
Yeah. So we say, right, even Iceberg, the tagline is analytics for petabyte scale. But that is only possible if you maintain your tables. You cannot work at Iceberg with petabyte scale without table maintenance. So the whole presentation today is about teaching what table maintenance does, what are the operation in table maintenance, and how to do it. So yeah, so if I divide table maintenance into two categories, one is compaction and one is garbage collection. In compaction, there are three major things. One is rewrite manifest. If you remember the architecture, there are a lot of manifest file that will keep on creating, so you need to improve that. Merging small manifest file into bigger ones, so you don't have, your engines does not read a lot of those manifest file to process. Then rewrite the actual data files to avoid small file problem. Merging smaller files into bigger data files, so the engine reads it efficiently, and there are lesser I/O operations on overall. And then finally rewrite positional deletes, right? So with Iceberg, when you delete the data files, it creates a delete tag, right, or delete file. So you need to also take care of those. Then there is garbage collection. Now that you're merging these things with compaction, sometimes snapshots are not required, right? So Iceberg creates one snapshot at every insert. Let's imagine a hypothetical world where there's no small file, there's no small manifest, everything is optimized. But yet, every insert is creating new snapshots. So the older snapshots are sort of useless, but it's slowing down your overall cluster because it's just there, right? Like, and getting some storage out of it. And then you have to remove those orphan files, which can be due to for multiple reasons. We'll talk about it. But yeah, overall, these are the categories of table maintenance tasks.
And also, just one note about it, it's about the manifest and about the snapshots. Just imagine that every single line or every single file, it is mainly on the HMS or in the catalog or inside the name node, it is closely 150 bytes, which does not seem too big, right? But if you have billions of it, you can reach out the limitation of the name nodes, or reach out the problematic part of the catalog as well, that you are not able to query effectively. So these type of maintenance is extremely, I would say, important to do, or to have some kind of schedule around it.
So let's start one by one on how, right? On what these operation does and how we should do it. So starting with manifest, rewrite manifest. What it does, it takes those smaller manifest file into a smaller number of larger files, right? So it's easier for a query engine to read. Each new manifest file still points to the same data files. So your data is not lost. It's just we are rearranging the pointers to your files, right? You simply just consolidating the metadata, compressing the metadata files. Why it matters? It helps in faster planning because metadata files are accessed by your query engines, right? And the more metadata files the engine have to process, the slower the query processing, right? So this step is very important for faster planning, lower I/O overhead. Now your engine does not need to read bunch of metadata file, like all are compressed, all data is compressed in one, and that creates lower I/O operation and simplicity, right? Keeps your catalog tidy. It does not add a lot of entries to your catalogs. How you do it? So in this case, I've taken example of Spark. You can do it via Hive also, you can do it via Impala also, right? So this sort of syntax is available in all in those query engines as well. I've just taken Spark for example as a reference. So you can run call catalog name system rewrite manifest. So this is a procedure call and your DB and sample, right? So So
But again, if you are using Hive or Impala, we have, I would say, a command or CQR command for this type of operation, and you can use it. It is up to you which part of you are you going to use. Even there is a Python script that you are able to use.
exactly. So you can, there are multiple ways to achieve the same thing, but yeah, this is a very important slide that you need to remember when you're thinking of overall, right? This part can be done with any query engine. So when to run it, right? So you generally run manifest file after a bulk load when there is a lot of data inserted into your Iceberg tables. It creates a lot of manifest file, many manifest lists, right? So post your ingestion job, maybe hourly or daily, whatever your frequency is, you should try to run this, right? When many new manifest files are created. So that's one tip. If you can afford some downtime or you have some time after your bulk load, try to run this manifest, right? You can run it on schedule also, where you're doing it on your off time. You can maybe create a airflow DAG or some sort of automation to schedule this and run at a particular time when you know you're not ingesting any new data. So yeah, or one tip, right? One gotcha. So you should always set a target file size by bytes so that when you're ingesting data, it is ingesting at a particular file size itself. So going next is example of this, right? And how this looks like. So let's say if you were initially here, right, at your S1, you had listed some manifest lists and you have some manifest files pointing to your actual data files, right? Same insert happens, you're here. Insert happens, you're here. Now, how does your manifest file looks like after the rewrite manifest operation, right? It creates a new snapshot with the newer manifest list and a manifest file pointing to all your data files, right? Now, your engine does not need to read multiple manifest lists to go through this. If you see multiple pointers, right? It has access or pointers to all your data file in this file, which is bigger and which is more efficient. Now you can actually clear these things out as part of your garbage collection job. So which makes the metadata much cleaner and easier to process. Yeah, so the best practice, right, when you think about the best practice. So this is very resource intensive, this operation overall, right? Rewrite moves actual data, it spikes CPU memory and disk usage. And it's also time consuming. So if you want to do this for 1 TB of rewrite, it might take some hours, right? And does have some upfront cost. So some of these things that you need to remember are here, right? Understand your data distribution. Check if your data is localized or any clustering is required, right? Use sort order if required. Run partitions, run partition wise if volume is high. So you run these job per partition. So if you have, let's say, 3 partitions, you run it one by one if they're not used. And you always do incremental optimizations rather than the whole table to keep making sure you're also running your operations, the access side of the data properly, and you're running these optimization on the background. So your data is always accessed and meeting those SLAs. Yeah. So the next step is the rewrite position deletes, right? What it does, so when you delete some data in Iceberg table, it creates either positional deletes or equality deletes. So let's talk about the position delete. So when you do a row level delete, it piles up in small files after the operations of delete, where, or merges, right? Which creates too many delete files sometimes, and it slows down query performance because whenever you query, let's say select star from this table, it is merging those two delete file and your actual data files to give you the final results. And it does add up to your overall planning and processing, right? So unoptimized delete files just bloats your metadata and drags down the overall read performance. So this is very important for that, right? And why it matters? It compacts small delete files, which creates lighter metadata and handles high delete workloads when you delete a lot in some cases. The syntax to it is here. You call a procedure call, rewrite positional deletes for files, and Hive and Impala also has.
Yeah, so the Hive and Impala is actually making in the compaction job, but also there is also a strategy that you can set it up for your table. So in the table, you are able to have the COV or MOR, so it means the copy on write or merge on read. Hive is using merge on read by default, so that's why when a new delete files is coming up, that if there is a folder, let's say in the same folder there are thousands of delete files, it is going to open it up and to create a result that is actually good for you. It's not always good. If you are using merge on read, maybe or the copy on write, in this case, yeah, maybe the insert operation or the delete operation will be slower, but at least actually you can save some time on the compaction side.
So yeah, with that, the last operation in terms of compaction is now we're going to the garbage collection side also, right? So now you saw this. Okay, I think I moved a bit early, right? Rewrite position deletes.
Next one. Here we are.
Yeah. So we are talking about expire snapshots, right? Now you saw the files that you create. Once you run the operation, there were a lot of older snapshots and older files which you have to clear. This is the operation to clear that, right? So Iceberg keeps every table change as a snapshot. Every time you insert something, every time you delete something, if there's even a compaction job or a rewrite job, it creates a snapshot. So what happens to the older snapshots, right? They are just lying there. They are an access pointer, which can also be used for time travel. But generally, if you do not use it, the best practice is that you do not have a lot of snapshots unless you need a very long time travel.
Yeah,
right?
some customers even actually just set for, I would say, 4 or 5 snapshot generation that they are storing. It depends on actually how they like it.
Exactly. So if you have a use case for time travel going back in Iceberg, make sure that you also think about that on how old a snapshot that you need. Otherwise, it's best to expire those snapshots, right? If not needed, because it just bloats your metadata overall. So if you expire snapshot, the benefit are that you save storage, you delete orphan data files that are linked to the expire snapshot, and slimmer metadata, right? And to do that, you have a Spark procedure that you can call. Same call catalog name system expire snapshot and the name. And here the trick is to tell the timestamp also, right? That will basically go and check whether at this timestamp, before this timestamp, there are any snapshot, it will clear it out. That will make your time travel also very easy. Let's say if you want to you have a use case that I, as a company, decide that I want to do time travel till last 7 days. So you make sure that you just say last 7 days, and all the snapshots before that will be deleted, right? So how it looks like in real life. So let's say till now, you have these insert operations, right? This is the latest snapshot that all your engines are referring to. Every engine is going to this and then accessing the data files, which are completely linked. Now these snapshots are sort of not used. What to do with them? You expire snapshot, and what it does, it just removes the overall linkage to this and expires your snapshot, while your data files are always preserved.
And I just also want to highlight that this is if you are expired the snapshot. After that, the time travel function is going to be only to manage till the first snapshot is happening.
Yep. In this case, only the first snapshot. Yes. So now the final garbage collection method, which is remove orphan files, right? Why it's needed? So let's say if your operations are failed, right? There are some untracked Iceberg metadata, which is just wasting space.
No, data files also could.
Yeah, data files as well, right? And the advantage of this is you reclaim your space. You reclaim your storage space. If you're on cloud, this is very important, right? Because you're paying for that storage. The removing files that are older than the cutoff avoids active data loss. You're just always referring to the newer ones. The syntax is pretty simple. Remove orphan files, and then a table name. And you can do a dry run also, by the way, of this if you want to just see how it looks like.
Also, one thing that we can extend here about this is, I would say, the code for remove the orphan files, but sometimes this type of orphan files needs to be said that it is older than, let's say, 1 day or something, because sometimes actually in this case, if you just see this type of code, it could be happen that there is an orphan files, but it is something it's happening in the time, and there is no reference for this file. So it is sometimes we even extend this type of code with that, say that these files is older than, let's say, 2 days or 3 days, because of course actually after that there is a timeout of the transaction.
So how it does look like, right? So let's say you had snapshot 1. After that you performed the operation which failed, right? So what will happen to the manifest files and all those things? So you just when you run remove orphan files, it removes this part while all the data is preserved overall. So yeah. To summarize this, right, and just to give you a high level on what the sequence of these operations should be. So here it is. First, you always rewrite your manifest files, then you run position deletes, then rewrite data files, expire snapshots, and then remove orphan files, right? This is to avoid any conflicts between two of those operations and making sure your data is secure and your tables are optimized. So yeah, so this is the overall summary. So now you know what table maintenance is, what it does, and how to do it. So now let's talk about how we at Cloudera do it, right? So now that you know the secret sauce, we'll show you how we have done beyond just table maintenance, right? So we have something called Cloudera Lakehouse Optimizer. In the talk yesterday, Bill Zhang, the VP for Lakehouse in Cloudera, he presented the service layer in our Lakehouse architecture, right? This is one of the service that provides automated table maintenance. You don't have to worry about performing all those options. All of that is automated. While it is engine agnostic. So it does not matter what engine you choose to use at a read side. This operation is completely done agnostic of that. You don't have to worry about where you're reading. You just have to define a policy, and it will run those jobs automatically based on the policy that you have defined, right? It has adaptive intelligence based on your usage pattern as well. So yeah. So this is what how Cloudera has automated the process. Once I think there was a question on how Cloudera is doing it. Is it automated? So yes, in Cloudera Data Lakehouse, this service is automated.
So the open source solution that we are providing, especially in the Spark, Hive, and Impala, is mainly the basic solution. You are able to compact it, but if you need something that is more automated related, these type of features is coming to the picture.
So yeah, so there are some stats that I wanted to show. So there are some impact analysis that we were able to test on a limited amount of data and run those TPCDS benchmarks, and we see that when the data is unoptimized, you can achieve this by the open source tools as well, like the one that we saw. But again, this is what we have done with CLO. So initially we saw that, okay, you have, let's say, the duration of the query planning takes, let's say, 73 seconds, right? After running all those operations that we saw, or maybe defining a CLO policy, we were able to get it down to 2 to 6x faster in certain cases, in certain data sets. And also save your overall storage by reducing the small files problems and removing those orphan files, etc. Which was able to get a significant decrease in overall storage and the query planning and performance.
Yeah, and these type of thing about that to create a non-performant Iceberg table, it's easy to create. So even I would say if you have couple millions of record that you would love to insert, and after that you would love to select it, there's, I would say, we also have in an upstream community there's some kind of test around it that were, as I remember, there with 8 millions of record, there were 1 millions of record that is deleted. If we are not compacted it, if we are not make the maintenance, it was 95 seconds to execute the query. If it is after the compaction, it is 2.2. It has a significance. So it is, I would say, the message here, it is when you are playing with the Iceberg table, it's always nice. But when you're facing some kind of, let's say, slowness, start to think about it, what kind of strategy that you made for the table maintenance.
So yeah, that was it. Thank you so much.
Yeah, and thank you for being here, and thank you for staying here for the long